Hello friends, welcome back to Scientific Blunders, where you learn the don'ts first. So, continuing our series on fluid mechanics today, we are going to solve a very interesting problem. Let me scroll down a little bit so that we can see the entire problem. And here it is. Find the velocities at x and y and the pressure difference between x and y. Okay, so here we have a tube. One end of the tube has a cross section AX, the other end has a cross sectional area AY. Okay, one end of the tube is labeled X and the other end is labeled Y, and the flow rate in the tube is Q, and this is volumetric flow rate. So if Q had units, it would be something like meter cube per second. Okay, and so we need to find three things. We need to find the velocity or the speed at x, we need to find the speed of the fluid at y, and we also want to find the pressure difference between x and y. Okay, so these are the three things we want to find, but we don't want to do this just for one case. We want to do it for two cases. The first case is when the tube is horizontal, and the second case is when the same tube is just rotated this way by 90 degrees. So x here comes here, y goes to the top, and now fluid doesn't flow from x to y but from y to x. Okay, so fluid is flowing down vertically, and we just want to compute the same things again. So we want to find vy for the second case, we again want to find vx, and we want to find the same thing, px minus py. Okay, so this is the problem. So let's do, this case seems like a little more complicated because there's the height of the tube as well, and the tube, we can assume that it has the same height. It's the same tube basically. Okay, so this is still h here, but I'm not entirely sure whether h will be used here, but let's do this problem first because it seems like it's easier. Okay, so how do we start? Well, we can assume, and that it's a default assumption that the flow is steady. Okay, the flow is laminar, so there's no loss of energy due to viscous forces, or there's no rotational flow anywhere. So it's just steady laminar flow. Okay, and when that is the case, we can apply Bernoulli's principle because total energy is conserved. The other assumption is that the fluid is incompressible, which means the density of the fluid is constant, okay, everywhere. So that means the volume that is flowing in per unit time should be the volume that's flowing out per unit time. And this is called the equation of continuity. So we have two equations. Number one, the equation of continuity, which comes from the fact that the fluid is incompressible. And number two, Bernoulli's equation, which comes from conservation of energy. So let's write down these two equations. Okay, the first one is that the flow rate, and so flow rate by default is volume flow rate here. Okay, so Q is nothing but AX times Vx. This is the input flow rate, and that should equal the output flow rate, AY times Vy. Okay, so Q is known to us, AX and AY are known to us, which means this is a simple division that will help us calculate Vx and Vy. So from this equation we say that Vx equals Q by AX, and from this equation Q equals AY Vy, we can say that Vy is Q by AY. Now just visually, by looking at this plot, what do we know about the relationship between AX and AY? Well, AX is greater than AY, right? It just looks bigger, so we assume this is kind of to scale. Okay, and so that means Vx, so if AX is more than AY, Vx will be less than Vy. And that makes sense, right? Because the tube is getting narrower and narrower, you expect the speed to increase in order to keep the same volume flow rate. Okay, So Vx is less than Vy. And let me also scroll down a little bit more. Now we also want to find Px minus Py, the pressure difference between x and y. So for that, we need to apply Bernoulli's principle between the points x and y. So Bernoulli's principle says Px plus rho g hx plus rho vx squared by 2 should equal Py plus rho g hy plus rho rho vy squared by 2. And just cleaning up this a little bit. Okay, now hx and hy, x and y are essentially at the same height. Okay, I didn't mention that explicitly, but you can see that from the diagram here. Okay, so hx and hy are the same height, rho is the same, okay, at all points, not just x and y, but any point in between. So essentially these two terms are equal, so we can cancel them out. And we are almost done, right? Because all we need to find is Px minus Py. And so if you rearrange this, that will equal rho by 2 times Vy squared minus Vx squared. And if you substitute the Vx and Vy that you got here, we should get rho q squared by 2 1 by a y squared minus 1 by ax squared. Okay, and we are done, but let's just understand this term a little bit. So will this term be positive or negative? Rho is positive, q squared is obviously positive. Because ax is more than ay, 1 by ay squared will be more than 1 by ax squared. Okay, so this entire term is going to be positive. And that means because px minus py is positive, px will be greater than py. Okay, so we have, we obviously solve the exact values, but let's, two important conclusions are that Vx is less than Vy, okay, and okay, so Vx is less than Vy, right, and Px is more than Py. So let's just understand and see if that makes intuitive sense. Vx is less than Vy, right, because as the tube gets narrower, you expect the speed to increase. And what did we say about Px? Px is greater than Py. Does that make sense? Yes, I think it does, because we've always been told that fluid flows from higher pressure to lower pressure. So that means if Px is greater than Py and the fluid is flowing this way, that would make sense, right? Fluid is flowing from higher pressure to lower pressure. So I think everything we did so far makes intuitive sense. And all we have to do now, let me just move all of this a little bit to the left so that we have space to continue the second part of the problem here. Okay, right? So what was the second part? We essentially have to solve the same problem. Okay, the q is the same, ay is the same, ax is the same, the length of the tube, or in this case the height difference, is again h. Note that h did not even appear here because these terms cancelled out. X and y were at the same height. But now this time, let's apply the same two equations. So number one, okay, is the equation of continuity. So q will equal ax times vx, and that should equal, so this is the outlet flow rate this time, and that should equal the inlet flow rate, correct? So that should equal ay times vy, correct? The outlet flow rate should equal the inlet flow rate because the density is same everywhere, so the fluid cannot be compressed really. So we end up with very similar looking equations. So vx is q by ax and vy is q by ay. Okay, now the same, this is the tube is the same basically, sorry, ay, the tube is essentially the same. So that means AY is less than AX, correct? AY is less than AX. That means Vy will be, or essentially we have the same thing as before. Vy will be greater than Vx, or Vx is less than Vy. Okay, let me box that equation. Now, the first time I did this, I remember I stopped for a second and was thinking, just checking whether I made any mistakes or not. Because see, this is under the influence of gravity. Okay, the fluid is flowing in the direction of gravity, and yet Vx is less than Vy. So imagine, fluid particle here is flowing downwards in the direction of gravity, but it ends up having a smaller speed here. So I encourage you to pause the video here and think about this, just like I did the first time, and because I think it'll really help you understand, how fluids are a little different from like rigid bodies that we did in other chapters. So assuming you have paused the video and thought about this, before we try to analyze any of this, let's also compute the pressure difference. Okay, so you have Bernoulli's principle again applied between the points x and the top y. So you have px plus rho g hx plus rho vx squared by 2 is py. So the same thing, there is a pressure term, there is a gravitational term, and there is a velocity term. Okay, now because the height difference between y and x is h, we can no longer cancel these two terms, right? You cannot cancel these terms. So instead, let's just simplify this equation to a form that is easy to solve or easy to simplify. So px minus py is rho g hy minus hx plus rho by 2 vy squared minus vx squared. Okay, now what is hy minus hx? First of all, hy is greater than hx because y is on the top, x is on the bottom, and the difference is h, the length of the tube. Okay, and what is vy squared minus vx squared? Well, we just solved that here, right? So on the whole, px minus py would be rho gh plus rho by 2, or let me skip one step and write the final expression, rho q squared by 2 into 1 by ay squared minus 1 by ax squared. Note, essentially this term here is the same term here, and you also have another term rho gh. Now we proved that this was positive. Okay, so this is the same term, this is also positive, and rho gh is also positive. Rho is positive, g is positive, h is positive. So the sum of two positive terms is also positive, right? So this entire thing is greater than 0. So that means px is greater than py. Okay, it's very funny the way I box equations. First I box it outside and then I drag it in. But okay, back to the problem. Px is greater than py. What does that mean? The pressure at this point is greater than the pressure at this point. Again, when I did this problem the very first time, I remember I stopped. This part gave me two unintuitive results. Number one, fluid is flowing vertically down, and yet Vx is less than Vy. Okay, that is the first result that was very confusing. The second result is fluid is flowing from y to x, but px is more than py. That's the result we got right here. Px is more than py. So what is going on here? What exactly, this seemed to make sense. Fluid was flowing from high pressure to low pressure, and as the tube became thinner, the speed increased. Here, fluid is flowing vertically down, but the speed is decreasing, and the pressure is also increasing. So it looks like the fluid is flowing from low pressure to high pressure in this case. So what exactly is going on? And I really encourage you to pause the video here and think about this, because this is really crucial to understanding Bernoulli's principle and the equation of continuity. So assuming you have paused the video and are back, let us try to understand. Okay, let me go down here. Okay, let me create like a new section so that we know this is. So now here, this is, we're not continuing the first part of the problem. This is just the, our time to understand what we did. Let's look at Bernoulli's principle. Okay, for any general case, or not like that, maybe a general case like this, or let me show the varying cross section. Okay, so this is point A, this is point B, and we assume laminar flow and steady flow and incompressible fluids and all that. And let's say there's a flow rate of Q. Okay, the first thing I want to say is Q would equal A, or the area at point A, times the velocity at point A. And if the fluid is incompressible, okay, that should equal the area of point B times the speed of point B, speed at point B. And no matter what, okay, if the flow rate is constant, if somehow you're able to keep pumping in fluid at Q, at a flow rate of Q, this is going to be true no matter what. So it doesn't even have to be a horizontal tube, it could be a vertical tube. Okay, you could have a tube that is like this. Okay, yes, you could have a tube that is like this. So even in this case, if the area of cross section is the same, then the speed is also going to be the same, assuming incompressibility. And this is a bit unintuitive, because we always think about when something is going in the direction of gravity, it is going to accelerate, right? But we have to remember that these fluid particles are not in free fall. They are not completely under the influence of gravity, because it's almost, you have like millions or trillions of fluid particles all all bumping against each other. It is not this, a fluid particle flowing from point A to point B is not the same as a point mass that is dropped. Point mass, similar to the problems we used to do in laws of motion. This is very different, because these, you have like millions of particles all jammed up against each other. So the mechanics are very different, and so we cannot intuitively, it might be normal to think that fluids accelerate when flowing in the direction of gravity, but that is not true. Okay, that is the number one learning from this problem that we just did, that just because something is flowing, a fluid is flowing in the direction of gravity, does not mean the speed will increase. Okay, so this was big learning for me the first time I did this. Okay, so let's write this down, because I think this is important. Fluid flowing in the direction of gravity just because a fluid is flowing in the direction of gravity does not mean that the speed will increase. Okay, and we just proved that here, right? So this, if there's a vertical pipe, then with a constant cross-sectional area, then the speed will also be constant, assuming that Q is a constant. Okay, so this is the first lesson takeaway. The second takeaway, okay, let's write Bernoulli's principle between 2 points A and B. So how do we do that? So pressure at point A plus rho g h A plus rho v a squared by 2 is pressure at point B plus rho g h b plus rho v b squared by 2. Okay, now, so the total energy at a particular point has three terms. There's a pressure term, this is called the pressure head, or something, not exactly the pressure head, but we can just call it the pressure head. This is the gravitational head, and this is the velocity head. Okay, so there are three terms that contribute to the energy. Now, Bernoulli's principle just tells us that the sum of these three terms has to be a constant everywhere. It doesn't tell us that for fluid to flow from A to B, PA has to be greater than PB. I can give you a very simple counter example. Assume there's fluid flowing in a horizontal tube, and that is very normal, right? We have seen this so many places in the real world. Fluid flowing horizontally in a tube, and there's there's point A and point B. Well, A and B are at the same height, okay? So these two terms will cancel. I'm assuming the tube has a constant cross-sectional area, okay? So VA will also be equal to VB. So these two terms will also cancel. That means that PA will be equal to PB, right? So pressure will be equal at these 2 points, A and B. And so if the pressure is equal, how is fluid flowing from point A to point B? Because we've always been told that fluids flow from high pressure to low pressure. Now I'm here to tell you that that is kind of a simplification that was given to us, but the way I like to think about it is that fluids, I'm actually spilling over to the next page here, but the second biggest takeaway from this exercise that we did was that fluids in general, we assumed, conservation of energy, correct? But in the real world, as you may have guessed, that is not always the case. So in general, if I had to make a very general statement, fluids flow from high energy to low energy. Everything wants to reach, everything wants to flow in the direction of lower energy. That is the nature of things. And I think this statement is true in general. Whereas we cannot always say that the pressure, we cannot always say that fluid flows from higher pressure to lower pressure. And we just saw two counter examples today. First one is this, where the pressure is equal yet fluid is flowing. The second is this, where the pressure here is greater than the pressure here, and yet the fluid is flowing from lower to higher pressure. Okay, so to summarize, we started off with two cases of these same tubes, and the first case we got results that made complete sense. Second case we got unintuitive results, and we also saw a few other cases, and the two biggest takeaways from this exercise are: number one, just because a fluid flows in the direction of gravity does not mean the speed will increase. The speed can remain the same, or it can even decrease, but it can also increase. Okay, so anything is possible. We cannot conclude anything just based on the direction of the flow. The second is that fluids in general flow from higher energy to lower energy. We assume a conservation of energy, but in general, in a real world problem, they will flow from higher energy to lower energy. Okay, and so I hope you found this video useful, and next time, hopefully, when you apply Bernoulli's principle and the equation of continuity, you have a little more perspective about what they mean. And so with that, I hope you found this video useful, and I will see you in the next video. Bye.